Well, we can try to start just to say a few words before, so Alexandra can start exactly at 9. So let me welcome all of you to this Mars parallel section experimental gravitation of the Marcel Grossman meeting. I thank you for participating to this, for your work to this section, and I hope you will have some good time for what is possible, at least in these conditions. You should turn on your camera when you talk. The meeting is being recorded. It has been already started, the recording. And we have 20 minutes each. And I will advise you a few minutes, 5 minutes before the end, so we can leave some time for discussions eventually. We have to be tight on schedule, also because this connection will be closed 10 minutes after the expected end of the section. So it's good to be on time. So please, Alexandra, just there are a few seconds left. You can start, and I close my microphone and the video.
Angelos, thank you. And let me just share my screen. Okay. Okay, dear colleagues, my presentation is on the topic of a man-made experiment aimed to clarify the gravity law in the solar system. This presentation was created in our research group of Institute of Gravitation and Cosmology of Rodan University. I, as you can see, not the first author for this research. I am the second author in charge of numerical computation, which I will talk about in my presentation. And the first author is our esteemed professor, Alexander Yefremov, who is here with me, but he is off camera. So this experiment, the idea of this experiment was designed by Professor Yefremov because at this point in time, unfortunately, we cannot see a valid experiment for general relativity theory, because recent experiments, in our opinion, have at least two weak features. First, we are dealing with isolated observations of very, very rare natural phenomena, and we have no influence over this phenomena. And mostly we study motion and merging of some really, really massive objects. And second, these objects are extremely far from us as observers. We can study binary pulsars. Those are observed at a distance of only 10,000 light years. But the actual sources, the sources of gravitational radiation, are determined at about 1.3 billion light years. So basically, we can study only rare phenomena and really, really far away phenomena, which leads us to studying the past, not the present. That, to our opinion, seems to violate the basic principles of any scientific experiment, which is the possibility to repeat said experiment and to deal with physical laws valid here and now. Yet, it is not, unfortunately, the case. Therefore, the claims about the absolute acceptability of Einstein's gravity are hardly convincing enough at this point. We understand that a repeatable experiment, which is designed to test very small effects of Einstein's gravity in the solar system, we can observe it, is a quite challenging task. In our presentation, we will try to demonstrate that such an experiment, or rather a series of experiments, aimed to specify the law of the sun's gravity with good accuracy is possible. The main idea behind this experiment is to use the so-called gravity assist maneuver of a space probe near a close planet. We have studied a lot of papers on space missions, and the gravity assist in those missions is a quite habitual instrument. So it's well studied, it's well designed, and we can actually use it here and now. So studying these papers, we paid attention to a great precision of the impact parameter value, which is the value of the close parameter pericenter. The shortest distance between the planet rendering the assistance and the spacecraft coming near this planet. On the solar system scale of just 100 million kilometers, the impact parameter is normally pre-calculated with a great accuracy of just 1 kilometer. This precision should reflect a great sensibility of the results of the gravity assist maneuver to the pericenter value. Small deflection here must entail great trouble for the mission if it's not calculated accordingly or any mistakes have been made. Unfortunately, we have found no sensible information about the gravity assist sensitivity functions. Naturally, we decided that if we can find it, we can determine. And so our research continued in that direction. First of all, we designed a scheme of a so-called standard flight in Newton's gravity of the sun, because it was naturally logical. And it represents a space probe's flight in a planetary system comprising several elements, which I'm going to highlight on this scheme. We had 3 basic elements beside the probe. It was a central star imitating the sun and 2 planets imitating the Earth and Venus. For simplicity, we assumed that the planets move in circular orbits, and other physical parameters of the system were very close to the observation data for real Earth, Sun, and Venus. Our pattern flight looks as follows. A space probe is launched from the Earth, from here. It can be also launched from the Earth's orbit, but here we can ignore the non-essential gravity of the Earth and so just proceed as there is no gravitational pull from our planet. From the launch point, at the initial zero time moment and azimuth of 0, the probe falls freely towards Venus by a Kepler elliptic leg. We call this track 1, and here you can see it in green. After a sufficiently prolonged flight, maybe 6 or 8 months, it arrives at the Venus gravity assist point here. The initial conditions are chosen so that the probe's perihelion azimuth is 180 degrees, and the gravity assist point has azimuth of 270 degrees, and strictly pre-computed pericenter value. The Venus gravity assist accelerates the probe so that after flight by another elliptic leg, it returns to Earth's orbit. Here you can see it in this dark green solid line. So basically till this point. At the assigned time, when it reaches this point in time, it sends a signal that can be researched by Earth observer. Thus, we can determine the probe's final position. Slightly changing the initial conditions, we managed to make the chosen pericenter shorter by 1 kilometer, and again let the probe move freely to the final position at the same time. Then we calculated the distance between the probe's final position with the pericenter difference of 1 kilometer. So basically those two points and this distance, which gives us the gravity assist sensitivity function for the chosen pericenter value. As you can see, we did it not only for Newton's gravity, subsequently changing our impact parameter for pericenter, we also did it for Einstein's gravity. Subsequently changing the initial conditions, we found the sensitivity values first analytically for 20 pericenter values, ranging from 18,000 kilometers to 8,000 kilometers, which means 12,000 kilometers to 2,000 kilometers in altitude between the probe and the Venus surface. We obtained the following results. Here you can see the functions that emerge. The sensitivity, again, as shown on this figure, is a non-linear function. At a greater percentile value, here at 18,000 kilometers, the sensitivity is about 20,000, which means that 1 kilometer difference in pericenter, for example, we had 18,000, now we have 17,999 kilometers. Throw the probe aside from the assigned final point at 20,000 kilometers. It's quite a large distance for this pericenter, but as you can see, at 8,000 kilometers, it becomes just enormous, even in space scale. The smaller percenter value thus gives us the sensitivity of about 10 to the power of 4, and the smaller we get, the higher sensitivity we get at 10 to the power of 5. So basically, the gravity assist maneuver works as a powerful amplifier of small pericenter changes, which are caused by some physical agents on its first elliptic leg, which was our track 1. We also cross-checked these analytical evaluations with basically a pure numerical computation of respective probe trajectories. We devised and designed an iterative program using Python 3. We chose the time interval of 1 second, and basically for each second, we calculated the positions of Earth, Venus, Sun, and of course, the Sun and the probe. So basically, we built each trajectory for each pericenter values on 35 to around 50 million points. So it was a great time. In real time, it would be like maybe a year and a half or 2 years of flight. The results of analytical calculation and numerical construction of those trajectories turned out quite close. It was, I don't want to say surprising, but it was exciting. The first physical factor to distort Kepler's track 1 in Einstein's general relativistic gravity, we made preliminary computations, and again by 2 methods, analytically and numerically. The general relativity gravity brings 3 reasons making the pericenter shorter. First, the general relativity ellipse slightly shrinks. Second, it's subject to a slow precession. And third, on a shorter trajectory, the probe arrives at the gravity assist points point earlier. So Venus is met a little bit closer, as you can see on this figure. Then, under identical conditions, the probe pericenter becomes about 40 kilometers shorter. Therefore, if the pericenter is 18,000 kilometers, then the final point must be detected at about 800,000 kilometers distance from the assigned position. This difference will be much more and reach millions of kilometers for shorter pericenter values. These distances are big enough to detect, and so their experimental detection by the observer on the Earth should indicate in favor of Einstein's gravity. Thus, we can actually determine the gravity law of the solar system. So, 2 independent methods of computation of general relativity-based deflection of the probe's trajectory final point from its classical position indicate that this can determine the difference, and this difference may be measured by the observer. Thus, Newton's gravity law can be distinguished from Einstein's gravity law, and the respective experiments seem feasible. In its standard flight, the probe falls freely in the gravitational fields of the Sun and Venus, so it actually behaves passively. The only action required from this probe is sending signals at the set time points. Therefore, the space apparatus can be a primitive body that is minimally subjected to effects other than gravity, thus achieving the least impact of any type of solar radiation or small celestial bodies, whose influence can hardly be considered. Additionally, the probe can be relatively small and mostly symmetrical. So basically, this space probe can be a ball of about 1/2 of a meter, weighing about maybe 100 or 200 kilograms, and equipped with a small transmitter. This probe is in our research called a space ball because it's basically a ball which does relatively nothing but sending signals. One of the most difficult aspects of this experiment is to consider all possible impacts on the probe motion through experiment factors. These factors include the gravity of the sun, which is not a point and a spherical body. Also, it radiates. We should also take into account all these effects. Also, we should take into account Venus' actual orbit, Earth, Moon, maybe Mercury, maybe other planets, especially Jupiter, maybe large asteroids. But still, in a real experiment, the probe motions can be detected and can differ from what we have calculated, but nonetheless, we can actually devise this experiment because we can perform it using the technology we have today. For example, it's not hard to find space labs that can send one probe, or better yet, a series of probes at some interval in time, which actually will give us the whole range of impact parameters. The probe itself is not a sophisticated station. It's relatively inexpensive, relatively being the keyword, and using the computing power we have at our disposal at this point in time, we can actually pre-compute all those effects. So we think that many cosmic agencies of different states and even private companies can afford the job. And we really hope that someone will be the first to do that. Thank you.
Thank you, Alexandra. Very nice talk. There are questions? I don't see hands. I have a question. Which kind of, I have a question by myself. In your opinion, which kind of things can be easily better studied with this kind of approach? There is a way to separate between theories or make some evidence of something, in your opinion?
We designed this experiment, this research, to differentiate between the Newton's gravity and Einstein's gravity. Because in truth, there's only one gravity law that actually governs the movement of celestial bodies and one theory of gravity. But yet we don't know which is the right one and which is the one we think is right. So if we actually make this experiment happen, we will see statistical data on the flight. And from the statistical data, we can determine which law governs the motion. So it's a precise experiment for this thing. Yeah.
Okay. So you want to test directly?
Yeah.
Basically. Good. Other questions? We have 2 minutes more.
Yes, if I may.
Sure.
Alexandra, there are about 50 years of spacecraft data available from NASA, ESA, and the Russian Space Agency. And there have been really a lot of gravity assist maneuvers of various satellites. Couldn't you just get these data and just statistically evaluate it? I mean, the precision of these orbital data is in the range of less than a kilometer. So it should be possible to see the effects you want to see also in these data that already exist. So why do you really need a new space probe to test this?
Rena, thank you for your question. The reason is our space probe should be passive. For example, the most recent experiment in gravity maneuver, at least the well-known recent experiment, was the Bepi Colombo. Naturally, all the courses, all the flights are adjusted in some way because we cannot just shoot a space probe, a multi-million or even billion-dollar space probe on an elliptic leg and hope for the best. Of course, we adjust the course accordingly. But in our experiment, we want to do just that. We want to launch those balls and do nothing and see how the gravity and the bodies will affect them. So yeah, that's the reason.
So you want a more ideal probe?
Yeah, no adjustments, no nothing, just the gravity in its purest form.
Okay, more questions? Well, if not, we have just a 1 minute shift. I think it is the time of René Sedmick, a parallel plate approach to force metrology.
Thank you very much. So we'll start right away. I will talk about CANEX, which is an acronym for Casimir Non-Newtonian Force Experiment. And to our knowledge, this is the only present experiment doing force metrology with the geometry of plane parallel plates, which brings quite a lot of advantages in such an experiment and allows us to not only measure gravity-like interactions, but also interfacial interactions like the Casimir effect. Regarding the motivation, I don't think that in this audience I need to talk a lot about lambda CDM, which you all probably know. It's just remarkable that with only 6 fit parameters, this model was and is able to predict a lot of cosmological observations, including the large-scale structure and dark matter distribution in the universe. But even if it has worked very good until now, there are caveats, and for this I refer you to another session that actually started yesterday. It's GB2 on tensions with lambda CDM, most notably the Hubble tension, where the Hubble constant can be determined from large redshift data from Planck, but it can also be determined from standard candles, supernova data, and other observations. And the difference between the two methods of evaluation is about 4.4 sigma. So this is really relevant. Another tension is the sigma 8 tension, where we have the normalized matter fluctuation amplitude, and again between Planck data and dark energy search lensing data and large scale structure data, we have, depending on the model, 2 to 4 sigma difference. And then something that is less known, the lensing torsion. This is about the spectrum of the lensing potential, and here we have a discrepancy between different evaluations of Planck data. So either you can derive the lensing potential from baryoacoustic oscillations, or you can take thermal and polarization spectra, and at large lensing order, about 100, you have 2.4 sigma, which is also not 0. So there are many more of these tensions actually. And again, if you're interested, go to this session. The point that I want to make here is just that there are tensions, and these tensions clearly are a sign that lambda CDM is not complete, and lambda CDM contains basically GR plus dark matter plus dark energy. So there might be new physics around. These tensions, they come in addition to long-standing problems, as for example, the strong CP violation problem of QCD, where the axion as an additional particle might be a solution. And we also have the cosmological constant problem that has received much less attention in the literature. Just to remind you, we have the cosmological constant lambda in Einstein's field equations that was introduced in 1918 in order to render the universe predicted by the GR to be static. Of course, as we know, Hubble then found that the universe expands, and now we know that this expansion even is accelerating. So we have a clearly measured value of lambda, which corresponds to a very small vacuum energy density. But if you take, on the other hand, seriously what quantum mechanics says, then you have to assign a 0-point energy to all fluctuating fields. And if you then calculate the 0-point energy or the vacuum energy for these fluctuating fields, then you get an infinite result, as we know. But the reasonable thing is then to impose a cutoff, and you can impose this cutoff either at the Planck length, which is the shortest possible length, or you could take, for example, the electroweak scale. But either way, whatever you do, you get a result that is by many orders of magnitude in conflict with the actual measurement. And this is known generally as the cosmological constant problem. Has been found more than 100 years ago, but as I said, has received very little attention in the literature. So the question is still open: why does vacuum energy not gravitate, but still contribute to measurable effects like the Lamp shift or Casimir forces that we can see in the laboratory? There have been recently quite a few propositions how to solve this problem, but there's no final answer yet. So it seems that if we want to understand dark energy, which basically is an ingredient for lambda CDM in a better way, we also need to understand vacuum energy. So we need more experimental evidence here. And if we are to search for vacuum energy, where could we search? Well, of course, it needs to be somewhere on the scale of the universe. And where we find it, is either at high energy, where we have quantum field theory, and we basically remove it by renormalization. This is tested by experiments at the LHC at very high accuracy, so that works very nicely. On the other end of the scale, we have it as dark energy and the cosmological constant, which is definitely not zero and not something that we can easily remove. And then we have this range here. And in this range, we also have vacuum energy effects, namely the Casimir effect and van der Waals forces. And this is also the range in which we can perform force metrology. Now, force metrology has a long history and is quite an advanced field. And why is this now interesting with respect to dark energy? Well, because most dark sector models, and that includes dark matter, so axions and axion-like particles, and also dark energy models, scalar fields as the chameleon or the symmetron, they would introduce non-Newtonian forces in this range at sub-millimeter separations. So if there's something out there at these low energies and we could find it there, it would be an additional experimental evidence for something that is actually happening at much larger scales. So our approach to try to measure this is very simple. We have a simple mass spring system, which creates one parallel plate and another parallel plate that is fixed. Now, this spring mass system actually looks like this. It's helical springs that are etched from silicon. This central area here is 1 square centimeter, so it's not that small. This is a photograph of a prototype where you see after etching the silicon. The Q factor is extremely high, which gives us a very high sensitivity. The lower plate is actually fixed. It's a cylinder from silica, optically polished to be ultra flat. Here you see an actual measurement of the surface. And the measurement principle that we use is optical. We have an optical fiber that can measure either the extension of this plate by the springs. By this, we can measure forces between the plates. And we can also detect the shift in the resonance frequency. And by measuring the shift in the resonance frequency, we can derive the force gradient synchronously to force measurements. There's another way to measure forces, and this is by doing pressure modulation. Some screened dark energy fields that have been proposed depend on the local energy density. So by filling, for example, a gas in here, we can change the energy density in a controlled way. And then we can make a differential measurement that basically kills the background of Casimir forces and electrostatics. So that gives us a higher sensitivity with respect to these forces. Parallelism is set using a capacitive measurement in this scheme here. We are now using a different one, but in the first measurements, we used the capacitive scheme that worked pretty nicely. And this would be a photograph of this setup as it was used for the first measurements. Here you see the sensor, it's gold coated. So it's actually quite a simple setup, but it works pretty nicely. A critical aspect in this experiment is vibrations and thermal influences. So the actual experiment is set into a small vacuum chamber here. And this vacuum chamber is suspended inside a larger vacuum chamber, which uses various techniques that we have borrowed from gravitational wave detectors, such as nonlinear mechanical filters. These are called geometric anti-springs, and against horizontal vibrations we have here a pendulum, and the vacuum chamber here filters out acoustics basically. So this was the first version of the setup that we tried to use to make measurements. And of course, as you know, if you have a long running experiments, contracts end and people have to move. So at the time that actually data was taking, we were taking data. The experiment was standing in Amsterdam and data acquisition was performed in Vienna, 1,200 kilometers away. Because you think what can go wrong, right? So you just take the data. And of course, something can go wrong. In this particular case, there was a rain pipe rupture and the lab was flooded. So the thermal controls were actually broken. And instead of the 10 millikelvin stability that we wanted to have, and what we also had in tests, we had then 500 millikelvin with the heating cycles of the building over the course of a day, as you see here. And there was another problem too, namely, the design was based on seismic measurements that were done in summer when Amsterdam is pretty dry, but in winter it rains a lot there. So there were additional sewage pumps in operation that increased the seismic background by a factor 5 to 30. So all of this, of course, affected our measurements pretty negatively, but still we were able to gather some data. And these are the first data that we took there. What we actually wanted to measure was the curves that we see down here. This is predictions for the Casimir force based on two different theoretical approaches. What we really measured was up here. The orange curve is corresponding to a parasitic AC potential that coupled somewhere into the setup, but as there was no physical access to the setup anymore, we were not able to remove this in time. But nonetheless, what we could demonstrate is that CONEX is indeed able to measure in the designated range of separations using parallel plates, and also that we can measure at the sensitivity level that we actually wanted, although there have been, of course, as I've mentioned, many technical problems. So this proof of principle is basically a success, and this was the motivation to move on. All the errors that occurred here were analyzed in great detail later on. The main error sources, as I have said, are vibrations. Here, the brown curves. On the left, we have, by the way, pressure or force. On the right, we have pressure gradient or force gradient. And another strong influence here comes from the yellow curve, which is the actual interferometric measurement that in turn receives a lot of non-trivial contributions from vibrations and temperature. So after moving to Vienna with the setup, we set out to improve it and to basically remove all these problems. And the new setup we came up with is this one. Now we have a two-staged isolation system instead of a one-stage system that we had previously. Again, this technology is borrowed from gravitational wave detectors. Here we have inverted pendula and regular pendula for horizontal isolation. We have two gas filter stages in the vertical direction. So this should give us an additional 20 to 40 decibel damping. Again, the setup is here. In the core setup, we also have a lot of changes. If you remember before, we did not have this shroud here. We have additional thermal controls that allow us to basically control the temperature of the sensor plate and the springs with an accuracy of roughly 1 millikelvin. Also, the lower plate is controlled differently, which allows us to have even different temperatures on both plates. This is interesting for some measurements. In addition, we also have now argon ion cleaning in situ, in addition to UV irradiation, and this allows us to remove not only biological dust that might be between the plates, but also residual hydrocarbons and also the patch potentials, surface potentials that are also a great error influence here. In addition, also we have now purely optical measurements, so there's no capacitive bridge anymore, and so there's also no parasitic AC potential, hopefully. Okay, so this whole system has been analyzed in great detail, and if we move back to our error budget, there has been recently a complete reanalysis, and these are the new results. Now, if you compare the results up here for the old setup and the new one, you see that there is a factor 100 improvement around distances of 10 micrometer. the main error sources are now not anymore vibrations and thermal influences, but it is corrugations, residual corrugations of the surfaces and residual electrostatic potentials, in addition to the actual resolution of the extension measurement. But what I want to draw your attention to is that there is now a new curve here, and this is the gravitational interaction between the plates. So using this experiment, we might be able to measure also large G, the gravitational interaction, at a precision of approximately 10%. And of course, if we would improve the sensitivity further, and there is still room for improvement, then we could make a measurement of gravity using test masses that are of the order of 10 milligrams. So this might be very interesting because it's a completely new regime. Okay, after presenting the new setup, there has been a flurry of new proposals what one could do with this setup, because we can measure interfacials and gravity-like forces. So I've not talked a lot about Casimir forces until yet, but this would be the first measurement, the first accurate measurement of Casimir forces at separations larger than 10 micrometer. And this would actually answer a few long-standing questions in the literature, but I will not go into detail here. What we could also measure is non-equilibrium radiative heat transfer, which is also quite a hot topic at the moment. Maybe more interesting for you in the light of dark matter, we could improve the limits on Yukawa-like interactions. So for example, for axions, where we have scalar-scalar interactions. And you see current limits come basically from Casimir experiments here on the left and from torsion balances here on the right. And in the middle between these two different ways of measuring, there is basically a gap because there are not many experiments being sensitive here, and this gap could be closed by CANX, which is quite nice. We could improve the limits here by an order of magnitude around 10 micrometer. What we could also measure is pseudo-scalar axion interactions. This would be a two-axion exchange between our non-polarized plates. Here we could basically reduce the present limits on the pseudo-scalar coupling constant by a factor 6 over a rather wide range of separations or axion masses. Then if we look at dark energy, just two examples. First, the chameleon. This model has been proposed as a quintessence-like interaction that is screened. The screening comes from a dependence of the interaction on the local energy density. So if we change the local energy density by such a pressure modulation measurement, we can trigger directly the chameleon interaction between the plates and remove all the background. The predictions are that the current limits, which come from atom interferometry up here and torsion balances here, can basically be bridged. So this entire open parameter space that we have here could be closed by CANX if we reach the designated sensitivity, which is basically saying that we could exclude the chameleon entirely as a dark energy candidate. Then finally, also the symmetron. This is a slightly more complex model. We have three different parameters here. Also, the symmetron interaction depends on the local energy density, so the same pressure modulation trick would work. Here we have just a two-dimensional cut through the parameter space, and the different lines are for various values of the parameter mu. So we can only compare, of course, values, lines that belong to the same value of mu. For CANX, for example, the prediction would be here 0.1 EV, that line, and the next current existing limit would be down here. So this is 3 to 4 orders of magnitude improvement, and the same is true for other values of mu. So there's a larger improvement possible also here. So in order to come to the conclusion, CANX is the first metrological plane parallel plate experiment. It is able to detect force and force gradient at the same time, which could give quite an advantage with respect to certain measurements. The proof of principle that we have performed was indeed successful, although there have been technical problems. We have improved our setup. It's currently being built up again. And we could measure for the first time Casimir forces at very large separations. And we also expect new limits on axions, axion-like particles, in general Yukawa forces, and also chameleons, symmetrons, maybe dilatons, and other forces. There's basically a lot more that we could do here. We could also transform the setup to a Cavendish-like setup with a screen between the plates. And in that case, we could improve the sensitivity even further, but that is open for the future. So there's great prospects. And with that, I thank you for your attention. And I want also to advertise the talk by Jacob Miko, who's talking about our second experiment, Q-bounds, that tries also to find limits on non-Newtonian interactions using ultra-cold neutrons at 11:30 in this same session. So thank you.
Thank you. Very nice talk, René. There are questions. We have time for 1 or 2 questions.
I have a question, if it's possible. Rudenko from Moscow.
Hi, Valentin.
Hi, Angela. So maybe I missed, of course, it's a difficult, very interesting experiment and setup, not trivial, but I missed only a stupid question. How could you check the axion presence? Because typically you need to have the magnetic field in this case. Maybe I missed, but please clarify at this point.
So what I was talking about here basically is just 2 versions. I mean, with the axion, you have scalar-scalar interactions, right? So you have a 1 axion interaction and we have non-polarized plates. So basically you can measure this scalar interaction. Of course, you have a background of Casimir forces and electrostatic forces, but this background can be removed since we measure over a large range of distances. So by fitting the residuals of the force measurement after removing the Casimir pressure and the electrostatic pressure, we can still detect Yukawa type forces here. So this is with respect to scalar-scalar interactions. And as you have correctly remarked, this is for pseudoscalar interactions that are actually spin dependent. But if you have a two axion exchange, then statistically, basically this averages out, and you have here the interaction constant to the 4th exponent, which means that you have 2 axion exchange. So then you don't need a polarization of the plates. And again, you are sensitive to these interactions. Of course, we cannot, using non-polarized plates, exactly say that if we would find something, that it is indeed GP or it is just GS. For this, we would need parallel polarized plates. Of course, this is indeed also possible if we have a magnetic shield in between. We are thinking in this direction, but this has not been worked out yet. So I hope that answers your question.
Okay, but I hope that your presentation would be available in the afterward in the work committee. And so thank you, very interesting talk.
Is everything recorded, Valentin? You will have a recording of everything. Okay, thank you again for this interesting talk, René.
Thank you.
Now let's move to Pravin Dahal, polarization rotation in geometric optics approximation and its subleading order correction. Please.
Can I start sharing my screen?
Sure.
Okay, so can you all see my screen?
Yes, all perfect. If you want to test your yeah, please, all okay.
Yeah, so yeah, I'm going to talk about polarization rotation in geometric optics, and yeah, if there is time, I will talk about like how to generalize to higher order corrections. So yeah, this work was done in collaboration with Professor Daniel Turner. So the motivation of this talk is the first one is the majority of this work is based on or considering about the quantum communications in weakly relativistic regime. So the recent explorations of quantum satellites have made
could to get it more loudly because it's a very small sound.
Sorry, I will try. So the recent explorations of quantum satellites has made quantum theory testable in weakly relativistic regime. So yeah, we want to know the errors in that regime. The next thing, or the next motivation is to know more about the properties of gravitational field by relating it with dielectric media, or the medium with permittivity and permeability. From that relation, like fruitful knowledge of analog gravity has been developed, so it's better to understand. Another is with the advancement of technology like LIGO and other detectors, we can geometric optics approximation might not be sufficient in the future, so we might want to go beyond geometric optics approximations. Geometric optics assume the wave of large infinite frequencies propagating in space-time, so we might need to correct for that infinite frequency limit. So and another motivation is the test of general relativity. So for the propagation of large but finite frequency waves, there is in the chord space-times, when they encounter lensing objects, then there might be splitting color dependent splitting as they propagate in the space-time, and this could be measured in the future experiment. So yeah, the structure of my talk is organized as follows. So I'm first going to talk about the setup, and then talk about how to calculate the special relativistic phase and the general relativistic phase or Faraday rotation, and then beyond geometric optics. So the structure of my experiment of our calculation is shown in the figure. So what we want to do is we want to calculate the polarization rotation as light propagate from Earth station to satellite coordinates. Yes, so we want to calculate the polarization rotation in two different settings. First, by considering only the relative motion between the Earth and satellite and ignoring the gravitational effect. And second, by considering only the post-gravitational effects up to second order post-Newtonian corrections and ignoring any relative motions on the leading order or up to second order post-Newtonian corrections. Those two effects does not mix each other, so the final result will be simply the addition of the phase or polarization rotation of these two different settings. So, and yeah, we assume the rotation of Earth to be aligned along the z-axis or the angular momentum along z-axis, and the Earth is rotating around the xy plane, and the velocity of the satellite, we assume the velocity of satellite to be arbitrary. And here we also take a reference guided star, which is denoted by Xi, SC here, because in chord space-time, while calculating polarization, the polarization or the meaning of polarization is meaningless without some reference directions because of the absence of global inertial frame. So we need this star which is infinitely far located, which we assume as infinitely far located. And the setup for the calculation geometry in general relativistic phase is we take parametrized post-Newtonian approximations, and we take this up to second order of approximations. When we use the formula for the gravitational force and for the equality of gravitational force and centripetal force for the moving satellite around the Earth orbit, then this second order, this epsilon will be comparable to velocity. So we can at least from here see that the velocity is of the order of 10 to the power -5 for near Earth environment, and this leading order gravitational correction, post-Newtonian correction, will be of the order 10 to the power -10 in the near Earth environment. And gravitational potential, this is this 10 to the power minus 10 epsilon square will be the bound and gravitational potential. To calculate special relativistic case, we want to calculate Wigner rotation or Wigner phase. The states unitary transformation of the states of elementary particles are obtained by the induced representation of Poincare groups. So states transform this way, where here U is unitary matrix, unitary transformations, and Ks represents some standard states, which we assume normally as 1, 0, 0, 1 or z-axis. Here Lk is the transformations of polarized Lorentz transformations, which transforms this standard states to earth frame, and lambda is the Lorentz transformation, which transform the vector k vector, propagation vector at earth frame to the satellite coordinate. And this thing can be decomposed into two factors, where one of the factor involve Wigner transformation. For massless particles, Wigner transformation can be written as the product of translation and rotation. As translation does not contribute to the phase and only rotation contribute to the phase, this thing can be written simply for massless particle as in this way, where omega bar, or the factor of rotation, Wigner rotation, is what we want to calculate, or the polarization angle we need. This is the change in polarization angle or earth as the light propagate from earth ground station to the satellite coordinate, and we want to extract this thing. So as I have mentioned before, so we take the velocity of the earth as velocity of the ground station in xy plane, velocity of the satellite arbitrary, and propagation vector as arbitrary. And the propagation vector at ground station can be related to propagation vector at satellite coordinate by series of product of two Lorentz transformations, in which one is the Lorentz transformation, transforming from ground station to inertial coordinate, where at the inertial coordinates, assuming at the center of the earth, and this one is the Lorentz transformation from that inertial coordinate to the satellite coordinate. So we have extracted the Wigner phase up to order v square over c square epsilon square. The expression is ugly, so I have put here the first order correction, and I have shown here the plot for two different settings. One setting is the earth is ground station is at equator, and earth is moving, satellite is moving around the polar plane, and another setup is for ground station at equator and satellite moving on equatorial plane, and the time t0 corresponds to the point where the phase when the satellite is directly above our head. So approximately the phase in this setup is 10 to the power minus 5 of the order 10 to the power minus 5. Now let's come to the phase due to gravitational field of the earth. For this, we use geometric optics approximation. So on the leading order, up to epsilon square order, geometric optics approximation is sufficient. So geometric optics approximation take the WKB ansatz and substitute this in Maxwell equation. So this is pretty well established. And yeah, we get equations for wave vector and wave vector or propagation vector and polarization vectors. So the equations for the propagation vector in geometric optics approximation is null, and propagation vector like travels in geodesic trajectory. Similarly, polarization vector is null, and polarization vector is parallel propagated with propagation vector. As we are doing calculations in near Earth environment, so it's stationary space-time, and we can decompose stationary space-times metric into the scalar, a vector, and a tensor in this way. And under this decomposition, so we can do this decomposition allows to calculate this, to reduce these 4-dimensional calculations into 3-dimensional calculations. So reducing this 4-dimensional covariant derivative into 3-dimensional form with metric gamma mn gives the following relation for this propagation and this polarization vectors. So this simply state that propagation and polarization vectors are rotated by an angle omega as they propagate along a trajectory in gravitational field, post-Newtonian gravitational field, or any stationary, or the gravitational field of any stationary space-time. So in the absence of global reference direction, we can assume a polarization triad, a coordinate triad, as we have reduced the problem to 3 dimensions. Now we can take a 3-dimensional coordinate in which one is the propagation directions and other 2 are perpendicular to propagation directions. So these 2 constitute a polarization plane. Thus, we can reduce the polarization vector in terms of these 2 polarization directions or reference frames. Differentiation and little bit of simplification by using previous relation for Schwarzschild space-time. Basically, post-Newtonian field, post-Newtonian gravitational field, up to 2nd order approximation is Schwarzschild field. So Schwarzschild field, simplified Schwarzschild field up to 2nd order approximation. So for differentiating this and substituting this thing for Schwarzschild space-time gives the change in phase as the light propagates from one point to another point. The post-Newtonian metric can be written in this form. And for this metric, as we are only sticking to epsilon square order, this rotation term, which is of epsilon cube order, the leading order is epsilon cube, so it's not important. And the trajectory of the light propagating in this space-time, this post-Newtonian approximation from in Earth environment can be written in this way, where n vector is the straight line joining Earth and satellite. So it's basically the trajectory without post-Newtonian corrections. And other thing involved correction terms. And here d vector can be interpreted as impact parameter or the nearest distance of closest approach. On Schwarzschild space-time or on post-Newtonian leading order post-Newtonian approximations, it's well known that the trajectory vector lies in a plane. Trajectory lies in a plane. So we can choose a polarization directions which is perpendicular to the plane of trajectory, and that polarization direction is constant as light travels from Earth ground station to satellite. And as I have mentioned before, we also need a reference direction guided by some infinitely located star. And we assume the light coming from star to Earth and satellite is affected only by the gravitational post-Newtonian gravitational field of the Earth. So we can just apply the previous formula which we have applied for trajectory from Earth to satellite. Here in this case also for the light coming from infinitely located star to Earth and ground station and satellite coordinates to get the reference directions in up to post-Newtonian approximation. Now we can define the coordinate triad. So to calculate polarization vectors, we need reference directions B1 and B2, and we can define coordinate triad if we have everything like distant located reference directions and propagation vectors. We can define coordinate triad in this way. They are mutually perpendicular, defining in this way. So after defining coordinate triad, we can integrate this equation for phase change to get the phase change as light propagates from ground station to satellite coordinates in post-Newtonian approximations. So here we assume a little bit different setup than in previous special relativistic case. We assume
3-4 minutes.
Oh yeah, thank you. we assume Earth and satellite both lying in XY plane. So we can write the propagation vector in this way, and star at arbitrary positions. So the location of star can be determined by two angles, alpha and beta, and location of satellite is determined by phi. Here alpha pi by 2 minus alpha is the altitude of guided star. So we can plug this relation, plug those things into this relation, and we can get arbitrary, very ugly angle for phase change in post-Newtonian approximation as light travels from Earth to satellite. So we can plot this relation for the visualization of data. So what I have done here is plotted the relation with, here are three arbitrary parameters, alpha, beta, and phi, which represents the position of star. Alpha and beta coordinates represent position of star, and phi represent position of satellite. So I have brought here phi alpha for various betas, and yeah, so this figure represents the Wigner phase in these different cases. Here are subtleties, like for alpha is equal to 0 and beta is equal to these values, and also when like reference direction is parallel to propagation directions, then the polarization directions are undefined. Because of our definition here, these things causes division by 0. So yeah, they are undefined, but yeah, in other case the polarization is defined. And so how can we mitigate those error in communications, during communications? So we can meet, as these errors are insensitive to states with zero helicity. So we can take two entangled photon states defined in this way. So if we like send one logical qubit as encoded two photon qubits defined in this way, if we use this type of photons for these logical qubits, which encodes two photon qubits for communication, then there won't be phase change as light propagates from Earth to satellite. So sorry, I can't go on this thing. So yeah, the leading order corrections take into account the terms up to epsilon square. So in both, in spatial relativistic phase, the correction will be of order epsilon, and general relativistic phase will be order epsilon square. And these both are gauge dependent phase, and they can be mitigated by taking some particular qubits for communications. Thank you.
Thank you. Pravin, there are questions? There's a time for a short question.
Could you clarify, in comparison with the general relativity, what additional element associated with your epsilon you introduced? It was not completely clear. Very briefly, could you comment it? What is the difference when compared with the general relativity in classical formulation?
So sorry, can you please ask the question again? I didn't get it.
So you presented some new theory with some small difference or correction in compared with the general relativity. It's right?
Oh yes, it was a gauge dependent phase in geometrical optics, in the limit of geometrical optics. So that phase has occurred, or that phase is just because of, we call that a gauge dependent. That's because in chord space-time there is no such things like global inertial frame. So we have to, at each point we have to define the polarization plane with respect to some reference frames. And here we have taken reference frame as an infinitely located star. And yeah, so because of that effect, so because of that, our definition or choice of local frames, we have encountered polarization rotation of light as it propagates from Earth to satellite. So,
okay, but so
did I answer your
completely theoretical calculation? There is no any comparison with any kind of real experiment with satellite and communication with satellite by laser light or radio light?
The calculation, the purpose for calculation is including the people are interested in calculating higher order geometrical optics correction, and the interest is because like higher order geometric optics corrections, there will be true phase in the sense that gauge independent phase, and those things has been related to those things might be observed, and there is speculation that those things might be observed in extreme gravitational field like near core black holes, rotating core black hole. But yeah, before like calculating those things, what we felt necessary is to know at lower order phase what is the phase due to like gaze due to gaze or the definition of reference frame. So it seems that that phase geometrical optics approximation is of the order 10 to the power minus 10, which is like beyond our experimental ability. But it's hopeful that the special relativistic phase, which is of order 10 to the power minus 5, that could be measured by experiment. So yeah, then it's just for reference.
Okay, thank you. Now we can move to the next speaker, which will be last one of this first part of the section. This is Alexei Belonenko, measurements of the gravitational redshift effect using the satellite SPECT-R in the Radio Astron mission. Please.
Okay.
Yes, perfect.
Hello, everyone.
You should. Okay. Okay. Okay.
2 seconds.
Yes.
Hello, everyone. I present an experiment on the precision measurement of the gravitational frequency shift using the Radio Astron mission. The spacecraft was launched in 2011, had on board a highly stable hydrogen frequency standards, a radio transmitter with a large network of ground tracking stations, as well as an orbital eccentricity of E equal 0.9. Due to the very elliptical orbit and hence the large modulation of the gravitational shift, we can measure the modulation of the gravitational shift with unprecedented accuracy better than 10 to power minus 15. We conducted special gravity sessions in the period from 2015 to 2018, when the hydrogen frequency standard on board stopped working. In total, more than 70 sessions were conducted, which, thanks to the accumulation of data, will increase the accuracy of the experiment with respect to a single frequency measurement. At the moment, the most accurate measurement of the gravitational shift was carried out with the Galileo satellites in 2020. The accuracy was 3.6 times 10 to power minus 5. However, Galileo satellites had a very small eccentricity of about 0.1. It follows from Einstein's principle of equivalence that the frequency passing through the potential difference delta U changed by the value C formula. Since we are checking the effect of the gravitational shift, we introduce the epsilon violation parameter, which, if the theory is confirmed, will be 0. The maximum relative gravitational shift is 6 times 10 to power minus 10. Briefly about the scheme of gravity sessions. Communication with the spacecraft is carried out in one-way mode. H measure contains gravitational shift because synchronized on-board standard, or two-way mode contains double Doppler and troposphere, but does not contain gravitational shift because synchronized ground station telescope standard. But due to the technical features of the spacecraft equipment, simultaneous communication in one-way and two-way mode is impossible. To solve this problem, switching between modes was used in gravity sessions. To receive the signal from the spacecraft, green band and push-in tracking station equipped with an 8.4 and 15 gigahertz receiver were used. A typical session had frequent switching between modes. If we interpolate the two-way mode data for the entire session and then subtract the interpolate data from the measurements, we get a raw gravitational shift in one-way mode, which is about 60 Hertz. We extracted a small gravitational shift from other effect that influences the signal sent from the spacecraft to the ground radio telescope. The first Doppler first order or Doppler second order, ionosphere, troposphere, instrumental effects, and very important standard drift. The delta F0 drift is a discrepancy between ground and on-board in frequency standard that changes over time. Our group has processed more than 5,000 one-way communication sessions to calculate the gravitational shift. Since the sessions only contained one-way data, we could only compensate for the Doppler effect with satellite orbital data and using the estimation compensation algorithm. The accuracy of the orbital data allowed us to measure the gravitational shift with an accuracy of 10 to power minus 2. We did not take into account the effect of the ionosphere and some of the instrumental effects. A significant problem for us was the compensation of the ionospheric frequency shift. The ionosphere is an environment in which the propagation speed of electromagnetic signals depends on the frequency of the sent signal. So it is not possible to remove it using a combination of one-way and two-way modes. However, we can take advantage of the ionospheric compensation methods used in GPS. For this, we need to know we take vertical total electron content. It means electron density data from EGS ionospheric maps to calculate the contribution of ionosphere using the formula bottom, knowing the elevation of spacecraft position and coordinates ground radio telescope. This slide just shows the depends of the ionospheric shift on the geocentric distance. It follows from the dependence that the greatest contribution of ionosphere falls on the perigee of the orbit, and on average turns out to be at the level of 10 to power minus 14. Accordingly, we must take into account the ionosphere correction to obtain a result better than 10 to power minus 14. To calculate the systematic frequency drift, we used separate calibration sessions that were conducted in parallel with the gravitational ones in the period 2015 to 2017. After reprocessing all the calibration sessions, we found 4-time sections that were best approximated by unique polynomials. We could completely eliminate the first order Doppler terms and the troposphere using a two-way communication mode, which contained doubled Doppler effect. For typical 60-minute sessions, there were 10-12 such switches. This graph shows just such a session in which the Doppler and tropospheric effects are excluded. The raw gravitational shift is 6 Hertz. In this graph, we just illustrated the change in row gravity shift throughout the session. To do this, we interpolated the data for the entire session and use a compensation scheme one way minus half of two way. The following result was obtained from gravity session using data from a standard WebNet frequency meter. We could take advantage of the two modes of operation and improve the accuracy of the offset measurement by an order of magnitude. However, further improvement in accuracy is associated with bad data quality from a standard frequency meter. To obtain this result, it was necessary to take into account the drift of the clock offset. At the moment, we have started the final processing of gravity sessions using high precision VLBA data, which is a narrow band signal recorded in the time domain. For the primary processing of records, we use an algorithm developed at the Jive Institute, a space spectrometer, and a C tracker. It is a digital spectrograph that splits our signal into short stationary intervals and builds a spectral estimate of the frequency on them as the maximum of the spectral density. After that, a frequency and phase polynomial is constructed over all intervals, which is then used by us to remove the trend in the signal recording. The trend appears due to the uneven movement of the spacecraft along the orbit. The applied method of phase detection is carried out only at large SNR, signal-to-noise ratio, which for gravitational sessions have a value of more than 55 decibels. After pre-processing the VLBA data, we can expect an accuracy of better than 4 times 10 to the power of -4. We have already processed several sessions using VLBA data and got optimistic results on error, but further clarification of some subtle effects is required. Well, thanks for attention.
Thank you. You are in perfect time. Questions?
Angela, maybe because I am co-author of this talk, maybe
Yes.
make some small comments.
Sure.
Okay,
Please.
so the problem is, so we have try to make effort to get a final result of the radio astronomy experiment, because we have already 3 years after the finishing of the mission. And the problem is that we, due to the switching, we use the duration of each record is very small, 70 seconds or 2 minutes or something like this. And due to this, we could not, using the normal spectrum analysis, reconstruct the error width of line, spectral line. So because it requires a more long duration of record. And we, in this situation, we propose another method. Alexei told at the end of his talk that we try to use the situation that we have. So we try to use the estimation of the error of frequency, the limit of Rao-Kramer border of Rao-Kramer estimation. Of course, it's from the experimental data, estimation of parameters, but it's possible to do it if you have the big, large signal noise ratio and very narrow band signal. Just these two conditions is satisfied. So that is why we hope that using this methodic at the end of this year, we will get the result close to the Galileo satellite.
I see. How much do you have to improve Just could you
No,
repeat?
the goal is initial goal, the formulation of the problem, to make accuracy of the violation of the Einstein formula better than they have got in the gravity probe A. It means a 10 minus 4. So we have to get the epsilon between the 10 minus 4 and 10 minus 5. That was the initial goal, and we hope that we will succeed.
Okay. Okay. Thank
So
you, Valentin.
I
Yes, please.
I wanted to ask a question. First of all, this is a very interesting experiment and also a very challenging one. I was wondering if you have an orbit that is more than 100 kilometers out there, then you do not have just the ionosphere, you also have influences by the solar wind. So it would be reasonable to equip the satellite also with plasma diagnostic experiments such as retarding potential analyzers or Faraday probes, and also to use data available on the solar wind to correct time resolved for the shift that you have in the runtime of the signal. Do you have any data available to do that for your measurement periods, or is there anything planned to have a second version of the satellite that takes into account these corrections? Because I guess that if you come to 10 to the minus 14, 10 to the minus 15 in the corrections, as you have explained, then also the solar wind will be very important for the corrections.
Thank you. Yes, but solar winds we taken into account only for orbital data about spacecraft.
Okay, maybe I will comment to you. It's absolutely valid, your remark. And of course, we understand that Alexei told about the main dominated hindrances in dominated shift. But there are very many very tiny hindrances. And so, and you told the cosmic you told cosmic ray and the particles and also magnetic field during the orbit. And so we have some theoretical aspect how to do this analysis. It has to be done, of course. But we had also experience how it was done by the Galileo group. So we are not new, but you are right in your remarks. Thank you very much.
Thanks.
Other questions? Are you happy or you want to reply? Okay. Other questions? If not, I think we have a break, 20 minutes break. So we will be back at 11:10. I will open the break. We try. I don't know what happens. Basically, I create these rooms. Well, I don't know how it works. That.
Okay.
Do we,
Angela,
yeah,
before you.
Yes, please.
Only Angela, I will not participate in the second part because I have another talk. But simply would like to greet you. The very pleasure to see you after the long period in the very strong. My cordial greetings to Nicola, and also I will communicate through the email.
Beverini, you mean? Mm?
Yes, Beverini.
Okay, thank you. Thank you.
Thank
I will
you very
tell
much.
him.
It's a pleasure.
Well, I don't know. I have opened this, but I don't know how it works. We have two rooms, but I cannot help you. I have understood that there is the way in which you can convene in one of the two rooms and talk together, but I don't have an idea. I'm sorry. If someone has, yeah, okay. So in principle it's possible, but in practice I am not smart enough to understand how it works. Wait. Okay, see you later. Hello, everybody. I don't know if exercise of the two rooms did work. I don't know. Something happened, but I don't know in practice if it was something useful. We can start with the first talk. Is Angelo Tartaglia, Dark Gravitomagnetism with LISA and Gravitational Wave Space Detectors. Please, Angelo.
Thank you. Well, I start sharing the screen. I hope you can see.
If you can, you should start your camera.
Oh, yes, sorry.
Yeah, well, to see some human.
Yes, of course. Here I am. Okay. Well, now the idea that I will present here is want to use the big interferometers which are being built or designed to sense gravitational waves and are placed in space. Now, let me start from the situation of space-time inside the Milky Way at the height of the sun. We assume, which is usually done, to be in a sort of dust distribution of matter where the grains are stars, and also we include a symmetry, which is the symmetry, the axial symmetry. So the line element I wrote there is written in cylindrical coordinates. The functions you see there, the elements of the metric tensor, are depending just on the distance from the center of the Milky Way and on the height above the plane of the disk. Which is perpendicular, of course, to the axis of the galaxy. We are inside this distribution. Even if the field is weak, we cannot just use the usual expression we would use if we were outside rotating mass. The functions there include many information. One is, of course, mass distribution, both the visible mass and the dark contribution, both the disk, the bulge, the disk of the galaxy, and the dark halo, which is much bigger than the whole galaxy. The obvious assumption is that everything is not depending on time. And the other condition is a symmetry condition. That is that there is symmetry, reflection symmetry across the galactic plane, which implies that the first order derivatives with respect to z of the various functions are all zero when z is zero. Now, this is the starting point in a sense, and let me go to the idea of gravitomagnetism. Actually, for the first approach, I'll show in a moment, the weak field hypothesis is not really needed. But if we want to speak in terms of a gravitomagnetic field, then we think to be on the tangent space to the observer, and around you, you should have weak field conditions in order to the description to be consistent. Now, in this approach, we know that time space, in this case, time angle term in the metric tensor, is maybe interpreted as a gravitomagnetic vector potential in 3 dimensions. And in the same approach, and using the base you see there here, you may evaluate a gravitomagnetic field just as you would do with a magnetic field. And the result is that on the galactic plane, this gravitomagnetic field would be perpendicular to the plane and would be written in terms of the functions and derivatives you saw there. Just to have an idea of numbers, the sun is at a distance from the center of the Milky Way in the order of 10 to the sorry, I'm just not. Okay, some units in 10 to 20 meters, and when you move around in the solar system up to the Earth orbit, you are displayed a displacement which is some units of 10 to the 11th meters, so that the relative change in the distance from the Milky Way, the center of the Milky Way, is 1 part in 10 to the 9, more or less. Now, one effect of the presence of this gravitomagnetic field is that when you send light along a spatially closed path, and for simplicity, we assume it is in a plane, the time of flight when you move on the right and on the left are different. The difference between the times of flight, the time asymmetry, is in our notation what you see here. In front, you have this square root of u. In practice, it is a term which accounts for the gravitoelectric field in the position where the observer is. This is at the position of the observer. The u, which again is the time component of the metric tensor in the integral, under the integral, is changing along the path you are following. This means that you have something which is not trivial in the result. But I repeat, the square root of u in front accounts for the use of proper time of the observer. Actually, if u is practically constant over the distances you are considering, you could easily include this term in front of the integral into the definition of time. I just left it in evidence there just for reasons of principle. Now, you calculate this integral, and if you are in weak field approximation, you can use ordinary three-dimensional geometry and apply the Stokes theorem. And so you are converting your calculation into a flux of the gravitomagnetic field of the galaxy through the area inscribed into the closed path you are considering. We have seen that the distances are changing, but changing at most in 1 part in 10 to the 9th when you move around in the solar system, in the inner solar system. If you calculate, write down the change in gravitomagnetic field of the galaxy when you move of a distance delta r, and you consider the relative change of the field with respect to its value, well, you have this apparently complicated formula. It is not so not difficult to see that this term here in front of delta r is usually much smaller than 1 over r. You could just verify this outside of a spherical rotating distribution of matter, for instance, for simplicity, but it is also true if you are inside the matter distribution. The change in BG, the expected change in BG, relative change is much smaller, is smaller than the change in the distance. It is smaller than 1 part in 10 to the 9th. Practically, you can assume BG to be a constant throughout your closed path for the light. And so the calculation of this flux is trivial. It's just a product of the value of BG assumed to be constant times the area, the enclosed area. And here there is an angle which accounts for the fact that the plane containing your closed path in general is not parallel to the galactic plane. So there is this gamma angle, and it is not perpendicular to the local gravitomagnetic field. Now, The situation for an experiment is a bit more complicated, since we cannot think to be on the sun and make experiments on the sun. You are on some laboratory or device or whatever, which is on the Earth orbit, and it is orbiting the sun on the ecliptic plane. This means that the formula which I wrote must be a bit complicated, because you have to move to the reference frame of the rotating observer. So you must include also the angular velocity of the orbital velocity of the Earth or the laboratory you are considering. But in general, the approach remains the same. You will have to account for the contributions coming from the galactic gravitomagnetic field, and also from the kinematical effects, kinematical Sagnac effect, because this approach is typical a Sagnac approach, which are present together with the proper gravitomagnetic field of the galaxy. The ecliptic plane is not parallel to the galactic plane, so there is again an angle with this alpha angle, which has to be taken into account. Now imagine that on the Earth orbit there is a triangle, a rigid triangle, and it is orbiting around the sun. Now, just to fix the geometry, the plane which contains the triangle in general would be at an angle, the angle beta, with respect to the axis of the galactic, of the ecliptic plane. And so you have this beta angle, alpha we defined just a moment ago. Then there is another angle, which is the one relevant for the experimental purpose, which is the angle between the direction of the axis of the Milky Way and the perpendicular to the plane contained in the triangle. This angle, when moving around along the orbit of the Earth, will, in general, will change and introduce a modulation in the effect you are trying to measure, which is the time asymmetry of the light rays traveling around your triangle in both directions. Let's come to the Lisa constellation. Lisa is indeed a triangle which is orbiting the Earth, it's orbiting the sun along the orbit of the Earth, and is also rotating about its own axis. The period of the rotation, the proper rotation, and the orbit are both 1 year. The area vector of this triangle has, say, the angle beta with respect to the north ecliptic pole, and the motion is such that the area vector describes a cone. So beta is always the same, but describing a cone, the angle with respect to the axis of the galaxy is fluctuating, and with a period which is 1 year. Here you see an exercise where, just to estimate some number, the BG is introduced with an order of magnitude that corresponds to the only visible part of the galaxy. Remember that the dark halo is much more massive than the visible part of the galaxy, so it is reasonable to expect an important contribution from that halo. And everything here is expressed not in terms of time, but of length, but the idea, of course, is the same. You have this simple oscillation due to the geometric reason I explained a moment ago. Now, how could actually work this idea of using Lisa? Lisa is a triangle, yes, it is a 5 million kilometers arm length. And this length is such that you cannot hope to work just as you would in a laboratory, just placing 3 mirrors on a rigid basis. Here you have spacecrafts which are freely falling, and they contain the masses which are the one used for revealing the presence of gravitational waves. These spacecraft and the arm length are not fixed, of course, not rigid, and there are changes of in the order of 0.4% or 10,000 kilometers in arm length, and also the velocity, typical velocity of the three spacecraft is not identically the same, but you may have differences in the order of 10 meters per second. This forbids you to use the techniques you would use in an actual interferometry measurements on Earth. You have to introduce post-processing techniques which synthesize the behavior of the system as if it were a real interferometer. And you would keep the accuracy at a level better than 1 nanosecond. These techniques are called time delay interferometry, TDI. There are many different approaches. There are also some approaches to the TDI with the same global constellation that may obtain different elaboration of the signal and obtain different results. One approach, which is used for control of the system purposes, is to mimic the output of a Sagnac interferometer as big as LISA is. This approach, this application, peculiar application, is equivalent to suppressing the gravitational waves signals if they are present, which is, of course, what is interesting in the case you want to measure something else. Indeed, the Sagnac effect is not influenced by the presence of gravitational waves, and here you are simulating a Sagnac. Now, we have to include, of course, the fact that you cannot expect—
5 minutes, Angelo.
Yes, okay, thank you. You should include also the contribution coming from the sun as a main perturbation. Here you have the form of the potential, vector potential gravitognetic contribution of the sun. We are out of the sun, of course. And again, an angling is included, geometry, which tells us that the axis of the sun is not coinciding with the perpendicular to the ecliptic. So you have to take into account also this. Now, another simple exercise shows that what you would measure in terms of Sagnac effect due to this effect coming from the sun would oscillate during the year, like you see in the picture. Last but not least, I should say, is that the Sagnac effect is not the only effect you could be interested in. There is also rotation of the polarization. We listened to a presentation before that spoke of this subject. I just tried here without details what you expect here as a sort of gravitomagnetic Faraday effect. If light is propagating along the line of force of a local gravitomagnetic field, you expect the polarization plane to rotate in proportion to the distance you have among two, let's say, mirrors at the ends. An advantage I can quote is that when you go back and forth, the return is not compensating what you obtain as a rotation when going, but it is cumulated because you invert the direction with respect to BG, which remains what it was. So there is an opportunity, so interesting here. Polarization effects are also taken into account in LISA for various purposes and for metrology purposes, and there are various techniques that could be implemented to measure and verify the behavior of the polarization vector of some signal, light signal. Now, I conclude now remarking and recalling that interference devices which have been designed for gravitational waves are also fit to verify and measure extremely weak different general relativity effects, such as those connected with gravitomagnetism. The experimental constellation of spacecraft in space give an interesting opportunity. So while building these systems, one should, and it is what we are trying to do, prepare the theoretical and practical instruments to measure the parameters which we are interested in. Now, work is in progress, both on the theoretical framework and with the aim of refining the experimental techniques viable for measuring the quantities we are interested in, and for elaborating and verifying what is buried in the data which can be collected. So let's see and go and see. And here there are a minimum number of references useful for people interested in this. And that's all. Thank you.
Thank you, Angelo. There is room for a small question. Well, I make a very small question by myself. What about your original idea to use this Vesagnac in space for dark matter search? Is something connected also with LISA, or no? It's not possible in this case.
The idea is that the effect first of all, you may expect that there is an effect coming from dark matter, because common wisdom assumes that we are immersed in a sphere, in a spherical halo, much more massive, up to 10 times more massive than the visible galaxy. And it is reasonable to see that this halo should rotate if the whole galaxy rotates. If it rotates, it produces a gravitomagnetic field. Now, the point is that to measure the effect of this field, you need an instrument which has a size comparable with the size of the solar system. You can really think to do this in the laboratory. So one idea was to use a big triangle using the Lagrange points of the Sun-Earth system, a proposal which has been done some years ago. And now having LISA, which is being implemented really not just on paper, LISA 2, which is smaller than the triangle, Lagrangian triangle, is 2.5 million kilometers of arm, so has a size which makes credible the idea to have something measurable. This is the framework of this proposal.
Okay, thank you, Angelo. Now let's move to Jacob Miko, Q-bounds, ultra-cold neutron bound by Earth gravity field, a tabletop search for hypothetical gravity-like interactions. Please.
Can you see the presentation?
Yes, yes.
Perfect. Okay, so I'm a PhD student at the TU Wien, and the Q-bounds experiment is located at the Institut Claude Langevin in Grenoble. And as the title says, we use ultra-cold neutrons that are bound on the surface of mirrors to search for hypothetical gravity-like interactions, and also dark matter and dark energy in all flavors that exist, basically. As you obviously know, a huge part of the universe is dark, and we don't really know how to do laboratory experiments to find dark matter or dark energy. And this is in part because gravity is a very, very weak force, which makes it difficult to isolate from other effects, especially if you have electromagnetic effects present, which drown out the effects of gravity. And this is why we use neutrons. They don't have any charge, and they feel gravity because they have mass, of course. And in comparison to other neutral particles, for example, atoms, they also have a very, very small polarizability. So you don't have to worry about van der Waals forces when using neutrons as compared to atoms, which makes the neutron quite a special particle, especially for precision experiments. And we use, in general, quantum mechanical methods to do precision measurements and investigate the behavior of the neutron in the gravitational field. In general, there are many, many different models of gravity and how this could be modified to accommodate dark energy. Basically, there are always different length scales and parameters that are model specific. And the neutron in Q-bounds is in size of the order of micrometers. So this is the length scale we would be very sensitive. Depending on the model we use, you can calculate the effects. Now I will shortly explain general terminologies on neutrons. There are thermal neutrons that have 25 millielectron volts in energy. And then there are cold, very cold, and ultra cold neutrons. They all are below room temperature in energy. For interaction with matter, there is the so-called Fermi potential or pseudo-potential that can be derived by coherent scattering of the neutron wave function on nuclei. And it turns out that for ordinary matter and ordinary elements, this is on the order of 100 nanoelectron volts. What this means is that matter can be used to store ultra-cold neutrons. There is a table, of course, there are tables with all of these energies. If you have a neutron that has a kinetic energy that is lower than the Fermi energy of the corresponding material, then it gets reflected under all angles of incidence. And here in this table, you can see this corresponds to velocities below 8 meters per second, basically. Also, the Fermi potential for most materials is on the same order of magnitude as the magnetic moment per Tesla, basically, and the energy that the neutron gains when you lift it up by 1 meter. The neutron source we use is PF2 at the ILL. The ILL is a research reactor, and it basically uses liquid deuterium to moderate the thermal neutrons that come from the reactor core. The neutrons then follow a curved guide, and then there is a turbine which contains a turbine blades which recede from the neutrons, and they get slowed down by this turbine, and we get from this you can get ultra-cold neutrons. On the right you can see the spectra. At PF2 there are 3 different beam ports, and they vary slightly in velocity and also mostly in intensity. And we are located at the UCN beam. So this is the red curve in this plot. Now, if you trap a neutron on a mirror, the 0th order approximation is that the wave function just vanishes at the surface. And if you go through the calculation, it turns out that the solutions to the Schrödinger equation are the Airy functions. And if you shift them appropriately, you get the eigenfunctions. Now to 0th order, of course, the neutron has to vanish at the mirror surface. And then it's quite easy to show that the energy of the nth state is given by the expression here. Now, if you look at differences between these energies, it turns out that if you go up to a state 6, then the frequency is below 1 kilohertz, and this is approximately 4 picoelectron volts in energy. There are characteristic scales. The characteristic size is about 5.9 micrometers or 6 micrometers. And then there is the characteristic energy. And this is approximately 0.6 picoelectron volts. And the value here is derived from the value for a transition frequency, which I will explain later in more detail. Now, if you have a superposition of different Airy functions or neutron states, and you let the neutron drop down a step of 40 microns, then you get a coherent superposition, and you get a time evolution, and this looks like this. This is not what we are doing currently in Q-bounds. Right now, we start out in the ground state, and we try to excite the neutron to a higher state. Now here, the neutrons enter from the left, and we have a neutron detector on the right that measures all the neutrons that go through the system. And this is a schematic overview of the Q-bounds experiment. Here you have 5 mirrors, which have different purposes, and the neutron propagates from all of the from left to the right again. And sections 2 and 4 are oscillating, and they are used to induce transitions. Basically, when the neutron comes into the setup from the left, it goes through section 1, and on top of mirror 1 we have an absorber, which is a rough glass plate, and this scatters out all neutrons that are not in the ground state. After section 1, we have a quantum mechanical state that is prepared in the ground state, and then we oscillate section 2, which induces a transition from the first in the 6th state here in this example. And the vibration is chosen such that we get an exact 50-50 split between the ground state and the 6th state. Section 3 is not vibrated, and there we have coherent propagation of the neutron wave function. And section 4 again is oscillating and is inducing the transition again. And the idea is that you choose the phase exactly right that you can excite the 50-50 split to the excited state. This depends on the phase between section 2 and section 4. If you have 0 degrees phase difference, then you excite the state. And if you have 180 degrees phase difference, then you de-excite the state again. This, of course, depends on the frequency. If you're not at the right frequency for this transition, then, of course, you don't excite anything. Then in section 5, again, we have a mirror with an absorber on top. And the idea is that if you have the excited state, it gets scattered out of the system by the absorber, and you don't measure anything through this setup. Inducing transitions basically involves changing the boundary condition for the neutron. And as you can see here at the end, this is basically how we calculate it. The experimental parameters that come from this are A omega, which is the velocity, the maximum velocity of the neutron mirror that's oscillating. We have it for section 2 and section 4, of course. Again, we have the frequency and we have the phase difference. There are additional effects like steps between mirrors, general phase offset between the mirrors, general frequency offset, and also a complete tilt of the whole system, which have to be kind of controlled and taken into account. Now, if you have some kind of new interaction which interacts with the neutron or with mass density, then you can just take your model and take the eigenstates of the neutrons in the gravity field and calculate the frequency shift. Just if you just do it to first order, then the formula is quite simple. Now, in Q-bounds, we measure differences, of course, of energies, which leads to the formula you can see here. So basically, we just have to subtract the energy shift. So if all states shift by the same amount, we would not be able to measure it. So we are kind of dependent on state-dependent shifts. And if you compare, then you get some value from your theory, and then you can just directly compare it with the experiment, and then you can make exclusions or discoveries. In practice, we have done this in 2018. There has been a paper published by Q-bounds, which was not using the Ramsey method I described, but the Rabi method, which only uses one vibrating mirror. And here you can see we have some effective potential for the particle model. In this case, it's a symmetron dark energy model, which involves a broken symmetry in vacuum, and in matter, this symmetry is restored. And from this, you get a kind of you get a decay of the field phi from vacuum to matter. This can be used then again as an interaction for the neutron. And from this, you can calculate the energy shifts. And if you do your experiment and you get some results for the transition frequencies, then you can constrain the parameter space of this model. Now here you can see pictures of the experiment. Focus to the right. Here you can see from the top the vacuum chamber in which the whole experiment is located. It is on top of a granite table, and the size is approximately 2 meters in length. And the neutrons here come from the top. Now, in general, we get the neutrons from the reactor. We have a monitor detector that kind of just measures the flux from the reactor, because this varies a little bit over time. Then inside the setup, we have a slit that basically does a velocity selection. If you assume classical flight parabolas, you get you can calculate what the velocity is for a given slit. And here to the right, you can see a measured spectrum. This is fitted with a Maxwell distribution, with a shifted Maxwellian distribution, and you can kind of get an idea of the velocities we have in the actual setup. This differs a little bit from the spectrum of the UCN beam at PF2, just because the geometry is quite constrained, and there are different geometrical effects that kind of shift the spectrum a little bit. Now, how to find the transition? First, you increase the vibration strength from 0 to some optimal value. In blue, you can see the transmission through the whole setup if you are at 0 phase difference between 2 and 4, and in orange in 180 degrees. And if you vibrate here at about 6 millimeters per second, then you get the maximum difference between the two. If you don't vibrate with the same strength for both sections, then you get a drop in the 108 degree phase difference as well. And this is used to kind of systematically exclude the difference in vibration for the two sections. Now, once you have the good vibration strength, you calculate your frequency. So you take your frequency and you scan the frequency, and the vibration strength stays fixed. And then you can take a few measurement points and get an estimate for the transition frequency. Now, this is a picture of the setup from further down. And now I will show you measurements from the last few cycles. In 2020, in August and September 2020, we measured this. On the top, you can see the increase of the vibration strength. And on the bottom, you can see a map of the frequency. This measures at different points to just show that we have the kind of behavior of the general transmission that we expect from the theory. And you can see this fits quite well. And if you then calculate the transition frequency, you get an error of about 0.16 hertz. We also did it for the transition 1 to 3. Here you can see the plot for the frequency sweep. And the error here is much bigger than before, because we basically got an equally spaced frequency grid, and not all points contribute in the same way to the transition frequency. So basically here you can see the function nicely, but the transition frequency is not as constrained as before. Then in 2021, in January, we measured again. And on the left, you can see the transition for a velocity interval from 4 to 14 meters per second, in the middle from 4 to 9.5 meters per second. And we did this to show that we can change the drop we see between the 180 degrees phase difference and the 0 degree phase difference. And we did a few more measurements, and then we made a parabola fit and calculated the minimum. This is what you can see to the right. In May, this is the cycle that is currently still going on. We wanted to optimize the drop in count rate, but it just did not work the way we expected it, and we got a drop of only 44%. What's important here is that if you look at all the frequencies, they agree very well with each other. And then you can go ahead and calculate the gravitational acceleration from this. If you do this, these are the 4 measurements of the transition 1 to 6 I presented. And if you calculate G, you get 9.812 plus minus 0.001. And if you calculate delta G over G, you get 1.05 times 10 to the minus 4, just with the transition 1 to 6. So this does not include the transition 1 to 3, which we have also measured. We're currently investigating systematic effects and trying to delete the preliminary statements over the plots, but this includes a detailed analysis of systematics, and this is still going on. This is why all the values I've given here are preliminary. In the future, currently we're measuring the transition 1 to 6 with a magnetic field. This can be used to investigate torsion and axion like dark matter. Later this year, we want to have a classical measurement taken at PF2 of the gravitational acceleration. There will be a test of the equivalence principle with Q-bonds, and in the far future, we want to maybe store neutrons to increase the measurement accuracy again. Thank you.
Okay. Thank you, Jakob. Very nice measurements. Questions? Okay, we have one question. Klaus, please.
Andrew Beckwith, I'm ready to go, sir. Hello?
Yeah.
Hello?
No.
Yeah, I'm ready to go.
No. Sorry, there is a question of Klaus Lemets. Just a moment, Andrew, please. Just a moment.
I've a short question. So, could you also use polarized neutrons so that you can make a test of the equivalence principle with for particles with spin?
So yes, we are currently doing measurements exactly with. So we have a guide field, and in theory, we could polarize the neutron beam before the setup, and to just use the guide field to just keep the spin direction for the setup. This is this would be possible, yes.
Okay, very interesting, and very, I believe, quite a difficult experiment. How long it lasts the measurement?
8 to 9 hours. So we have 10 millicounts. So for one point measurement point, we have millicounts count rate. So to 20 for the best case, and especially if you go to a low velocity interval, the rate goes down very far, and you have to measure forever to still see the kind of dip.
Okay, thank you. So if there are no other questions, we move to the next speaker, which is Andrew Beckwith.
Yeah,
review of tokamak physics and gravitational wave condition in relative conditions.
I'm going to get the screen. I'm going to get the screen up.
Sure.
Okay, I'm sharing the screen. Okay.
Not yet.
Do you see the screen? Hello?
Yes. Now,
you
yes.
See the screen?
Yes, please. Oh, well, it is too big, Andrew. Can you shrink? I don't know. I don't see.
Oh, sure. I can shrink it. It's easy.
Okay, good.
I did it. All right. Let me just proceed with this. All right.
Yes, sure.
Okay.
Go ahead.
Okay. Review tokamak physics and conditions for Rayleigh condition for 10 to the minus 26 reduction frequency predictions as to what may be obtained in ELISA gravitational wave measurements from 10 to the minus 4 hertz down to 10 to the minus 16 hertz for ELISA. Now, actually, Fang Yu and other people in Chongqing had gone over to a tokamak and Hefei, and they've actually have made preliminary inquiries of this. And the idea was to come up with something that would be, to say, equivalent. That would be equivalent, let me see. We consider inverse procedures predict what may be obtained in ELISA near Earth orbit and gravitational wave frequency. Among other issues would be the duration of the gravitational wave pulse observed in ELISA measurements, the relative degree of noise and signals observed by ELISA, and this the device of a step down frequency from about 10 to the minus 10 to the 19 hertz. In the earlier universe are 10 to the 10 hertz down to 10 to the minus 4 hertz to a low at 10 to the minus 16 hertz, as could be ascertained by ELISA. We use the tokamak in order to obtain gravitational wave signals of the 10 to the minus, 10 to the 20, 10 to the 25 or 10. ELISA would observe the way that guesses as to the turbulence of the ELISA signal, how to consider and prepare for an inevitable stochastic noise in the signal, as well as guesses as to the sources as to the noise and the duration of the signal, which may be observed by ELISA. We do this, as was mentioned before, using Griszka condensation amplitude for the gravitational wave due to the plasma in a toroid. We generalize the result for tokamak physics. We obtained evidence for strain values at the 10 to the minus 25, 10 to the minus 26 H in a tokamak center. The gravitational wave frequency by tokamak are due to plasma physics interactions with the tokamak toroid, but can be, with an application of common sense, allowed to look as to what to look for in ELISA in its commissioning and gravitational wave runs. So I'm going to keep this very brief. The author is given a decay millions of Planck-sized black holes in it could generate gravitational waves to break up of black holes. So that was the idea. And then what we can say is the duration of an observed signal is relative noisiness and stochastic noise contributions, which are covered in reference 5. In addition, the generation of gravitational waves tokamak is commensurate with the ELISA data as a step down of 10 to the minus 25, 10 to the minus 26. This is talking about the frequency due to 60 or more E-folds may allow for a review of adequate polarization states for gravitational waves, which may or may not need higher dimensions to be in fidelity with the data sets obtained. Having said that, what are the justifications for using the tokamak? So what is our inquiry good for? Determination of the fidelity of the E-fold value of 60 in the Big Bang. Issues of initial gravitational wave polarizations may be configured at the start of the Big Bang. Determination of the relative stability of the production of the gravitational wave signal, i.e., if we had a tokamak running, the resulting gravitational wave amplitude and a characteristic of the signal are stable over a long-time interval. Does this imply stability of the ELISA signal over time and space? Can you make an equivalence? Likelihood of noise and stochastic fluctuations in a produced gravitational wave signal. As A, B, C, and D were determined as the tokamak and gravitational waves, we may be able to infer what to look for and to model when examined directly what a ELISA gravitational wave signal set of characteristics may be inferring at the early universe conditions. Having said that, let me go to the to a tokamak. Now, this was done by Griszka condensation, and this is the amplitude of gravitational waves. This is done in 1975. This is the geometry, and this is the flux. But that's the first order effects. But what you have is that, so you'd actually have gravitational waves, you'd have something that would not be a smooth cylindrical donut. You would have something that would be wavy curves because you'd have essentially a semi-chaotic plasma. All right, now, then, which is right here, we have the amplitude. This is a better estimate of the gravitational wave amplitude. And then I had, this is the current Ohm's law. This is the E field. And E is perpendicular to B, the velocity is perpendicular to B at the first approximation. That is what you would get. Let's say the contribution is a gravitational wave generation far larger strength is one does not have the velocity of ions and plasma perpendicular to B fields in the beginning of tokamak generation. And here is just simply the ion density. And what I did right over here, and it's a fairly long derivation, is that there were two strain values that were obtained when you were looking at what you might call ion flow to a tokamak in a first and a second term. And this had to do with the relative strain. So the first term is something which is Griszka condensation. and this is what you would get. This is the estimation of the plasma frequency. And then you'd have the second term, which actually would be 10,000 times larger than results that you would get otherwise, what Grishkuk and Sashin did. And this is equation 8. Now then, enhancing gravitational wave strength, amplitude versus utilizing a burning plasma direct current. The way forward is to look at induced E-field contributions. That's Wesson. This is typical. And what you would get, you get a current flow. And this is actually due to the geometry of the was E and B fields. And then you've had numerical drift of drift. And so when you would still get is that at the end of the day, is that you could get a second term strain, which would be roughly 10 to the minus 27. The second term, the first term would actually be much smaller. And there's a lot more to it than this. But let me just go as to why I even brought this up. What can we say about a plasma generated signal creating gravitational waves relative to ELISA? Well, the situation is that what you could do is that you could infer a step down to say in a relative frequency, what you were getting, which is the relative frequency you would be getting would be 10 to the 25th times larger than the Earth orbit. So you would get something like a 1 hertz versus 10 to the 25 other hertz. But that's something you might be able to get in the early universe, but you might be able to pick it up. But much of the other characteristics which you could get from the tokamak would be an overlap with some of the characteristics you might see in a gravitational wave signal by ELISA. Now, that's what I was doing. There's more to it than that. And here is some of the work that's been done right over here. Here is the one. This is actually a long pulse and confinement plasma regime experimental conducting tokamak. And this one right over here could be with certain adaptations used for gravitational wave signals. Here is the polarization. Now, with that, so I really don't have very much more to say. And I really don't have very much more to say than this. I pretty much said it. There's a lot more to it than what I have said, though. Is it clear relatively so far what I was trying to imply?
Mm-hmm.
What?
Okay. Thank you. So thank you, Andrew.
Yeah.
Thank you, Andrew. Questions?
My computer is acting up right now. My computer is acting up. It's not you. My computer is acting up, and I may have to just I don't know what it's doing at this point. But anyway, I didn't have very much time, and I didn't have very much time, and that was pretty much it. And so then, which is that with that, how do I get this thing open? Oh.
Yeah, but you have uploaded your contribution in the website, so interested people.
I don't know what it's doing at this point. Okay. Yeah. Anyway, which is that I'm done with this.
Okay. Thank you, Andrew.
But I'm saying the idea was to come up with something that would be roughly consistent. It'd be roughly consistent. Okay. And I hope that I have done this. But anyway, is that I'm going to have to turn in a relatively long a relatively long explanation of what I glanced over in this for conference proceedings. And I can't do that about the actual thing about the one-to-one. The frequency in ELISA would be completely different from the tokamak, but the characteristics of the behavior of it would be actually very similar. And if you just simply did a downscaling using, you know, 10 to the minus 25th, you know, more, you might be able to infer quite a lot from it. And that's really was what I was trying to say.
Yeah, okay. Thank you, Andrew. Do you have someone which has questions? But in any case, you have.
Yeah, I have to go.
Oh, okay,
how do I
okay.
get this thing off?
Okay, okay. Thank you.
I have to turn this thing off. I don't
Oh
know
well,
how.
I think I can do for you.
You
I
can
think.
just simply just kick me off the system.
You think so? I don't want to do stop sharing. Okay. 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 Thank you, Andrew. So we can go to the last talk of the section, which is Gary Stevenson, which will talk about the gravitomagnetic field generation using high-performing material in mass device. Please, Gary.
Thank you for the introduction, Angela. So I presented 3 years ago at Marcel Grossman 15 a notion for using a superconducting magnetic energy storage device to potentially generate a gravitomagnetic field that could very well create a measurable field that could be done in a lab. This was a very large device, very difficult to build. However, recent derivations have come to light that might shrink the device. So this was the impetus for me returning to Marcel Grossman with this concept. I'll go over a little bit where that change in derivation came from, the motivation for getting me to return to the conference, the new physics involved in that, what's changed since Marcel Grossman 15. Then I'll review the concept of forward coil, which is a coil of flowing matter that creates a gravitomagnetic field invented by Robert Forward. The recent evolutionary changes in superconducting nanowire technology that is enabling us to consider using this for a gravitomagnetic device. Why high permittivity materials in conjunction with mass flow might improve and strengthen the effect, gravitomagnetic effect. A little bit on the gravitomagnetic force equation that Forward first introduced. The currents involved in these SMAs or superconducting magnetic energy storage devices and other forces then involved from that mass flow or current. Recent news here on unexplained aerial phenomena was released by Director of National Intelligence in the US. And for those not following the news, included in this report were 3 investments were recommended. A collection strategy, seeing these devices better and measuring them better. A tech roadmap on how can we do research and development to explain these devices, and a program plan. This work has already been going on in the form of a program called ATIP, which was to study this phenomena in terms of, can we use science to explain these devices? So in particular, funded areas included space-time metric engineering, traversable wormholes, anti-gravity for aerospace, metamaterials for aerospace, and gravity wave communications. This particular program ended a number of years ago, but there is a civilian equivalent to the STARS Academy that continues this work, and a number of people in the US have been involved in that activity. In particular, the interest arose very vividly in 2004 with the Nimitz sighting in the infrared. These particular UAPs were dark, which means they had no black body radiation, or at least their black body radiation was no longer in the infrared. However, in the visible sensors, which I did not depict here, they were glowing white. So the thinking is, or at least one hypothesis is, the black body radiation got upshifted from the infrared to the visible, which implies a blue shift that implies non-Minkowski space. In other words, these phenomena may be associated with general relativistic effects where there's a blue shift associated with the devices. So some of the work trying to explain this was done by Jack Sarfati very recently. I've depicted a screen snap of his work with his permission and recently represented this at an aerospace conference. And this introduces an S term that you can see here in Einstein's fields equations down at the lower equation I've circled, where this S term here enhances the strength of the effect, and the G over C to the fourth, here the C is not the actual speed of light in matter, it's the speed of light in a vacuum. So this is the constant, C, where C squared is 1 over permittivity and permeability. The references he cited to derive this S term included the Lenz soliton warp drive reference that came out last year, in which you can find in Einstein's field equations soliton solution, which does include a blue shift and a red shift. And in terms of formulating this effect, it can be formulated as a energy momentum tensor effect. And that's essentially a first order tensor term. And he uses this equation 26 to describe that. And that's essentially what this S term is. So this does describe, and this depicting more of an Ackleberry type warp drive versus the kind that you would see in the Lenz soliton solution. But nevertheless, you get the idea that there can be a blue shift and a red shift associated with these devices that potentially could isolate any payload inside the device from the very strong gravitational effects used to propel it. So this S term then affected my work and came in right here, where the forward coil that I introduced 3 years ago, Marcel Grossman, that represents mass flow here. This S term can be used to scale the strength of the effect, and thereby shrinking the device and shrinking the coil count and the flows necessary to see a measurable effect. Also improving the effect is the shrinking superconducting nanowire technology. We can get a couple amps in a micron wire. This is the work of William Reichen in Japan, and I went over his work extensively in my paper 3 years ago. This depicts the electron flow. It would be a cross-section of the toroid, and this would be one loop in the toroid, and this would be the change in mass flow associated with an electron. So the idea is to have a torus of coiled wire, superconducting wire that flows electrons, and these electrons then are generating your mass flow. This is just sectioning the torus so we can look more closely at it. This is a 10 centimeter geometry versus a 10 meter geometry that I showed 3 years ago. So a much tighter and smaller geometry with much fewer windings should be required here. This particular section shows cross section of the torus where the windings and then any core, probably just a vacuum core for the purposes, since we're not trying to store magnetic energy, we're just trying to get a mass flow. So this would be a cross section of the coil here. A tighter look at the cross section of the coil just to get an idea of how many windings we could include. This is a calculation of the winding count. We would wind up per section with 1,700 windings, 28,000 total. Non-relativistic force here generated by each circular motion of each electron is calculated here for a given voltage, 16 kilovolts in this case. The angular acceleration of the electron for the geometry I've described. And that gives you about a nanonewton per electron for the mass flow in terms of centripetal acceleration. And the number of electrons can be calculated for a given current density. You want to stay under the critical current density for superconducting mass flow. So for the materials that I've been looking at with William Rankin, 250 mega amps per meter is the max, which for the geometry we have is about 2 amps. So for 2 amps, this would be the number of electrons circulating in any given loop. Then you can calculate the total mass flow by the number of electrons times the mass flow per electron. It gives you something in the order of millinewtons. That is, though, the centripetal force, not the gravitational force. Then the coupling to the gravitational force calculated by this equation given by Forward, which is also impacted by the number of loops, giving you 0.12 newtons, and then the S term, and then these coupling constants associated with gravitomagnetic coupling, and then the relative gravitomagnetic coupling. Questions then are, what are these terms? S, eta naught, and eta R. If we go back and look at Sarfati's formulation of Einstein's field equation, we see the S term back in here. We see the possible improvement factors of eta naught, eta R, and S. The S depends upon the geometry of matter. There is very complicated geometries that are being looked at in terms of metamaterials, but for isotropic properties, isotropic materials, I should say, the properties of isotropic materials are permittivity and permeability. High permittivity turns out to be important here for a very high permittivity devices such as 10 to the 8th. That could give you a best case coupling constant. But then we also have to determine what are eta sub naught and eta sub R. And there's a range of opinions on what eta sub naught is. General consensus of my reviewers in the past has been G over C to the squared. If that is true, then we also have to determine eta sub R, or potentially even measure eta sub R for various materials. So concluding then, it could possibly be measurable if we used very high current density superconducting nanowires to build a forward coil, to build a device with toroidal current flow. This then could be used to do a potentially measurable gravitational field. We could then get a better handle on the relative gravitomagnetic permeability of various different devices and better describe the strength of the effect. Right now, it's pretty up in the air in terms of what this gravitational force could be, but it could be potentially nanonewtons or even micronewtons. Suggested research in the going forward, better model. I've done some very rough calculations, but better model the gravitomagnetic effects for various wire permittivities. If you look at the insulation of the wire, what are the permittivities of it? Because it's closest to the wire where the greatest effect is. And then possibly build a forward gravitomagnetic coil to see if there is an effect, and even close the loop with a gravitomagnetic coil to see if there's a Lenz's law. Would it be charged by a gravitational field? That's all I have. Any questions?
Yeah, just okay. Questions, please. Oh, Renee, please. Renee. Go ahead, Renee.
I'm not. You might still be on mute. I'm not.
Ah, okay, because it was your hand was on. No, just a question. When do you think you will make this real coil?
Yeah, there's no current funded effort. So one of my motivations for presenting this would be to get enough interest to see if someone would be interested in building it. I don't know of any funded efforts to build this right now, but I think it would be very interesting to get a couple different labs to build such a device to see if we could see a measurable effect.
Okay, thank you. Rene, I don't understand if you have a question or not, because your hand is raised. Okay, if no other questions, I think we can thank everybody for being here and for all the nice talk, and we convene again on Tuesday afternoon. Thank you, everybody. The section is closed. Klaus, please, if you want to say something, I don't know. So we can close the section, I think.